Thank you so much, everyone. Thank you for being here. It's purely a privilege to be surrounded by so many experts in mechanical ventilation, but also really pioneers in flow control ventilation. And my task after those impressive cases presentation is try to unravel why flow controlled ventilation is such a unique ventilation mode. Is it so different than other conventional ventilation modes? Oh, sorry. So my task is to unravel why flow-controlled ventilation is such a unique ventilation mode. And especially, like you said, why is the tidal volumes are moving based on compliance differences, based by the physicians. And it's purely because the flow-controlled ventilation is a pressure-controlled mode, and this means volume will change and the pressure stays the same. But I will explain this. But before I start the presentation, I would first like to express my deepest gratitude to Professor Chadburn. And Professor Chadburn supported me in an invaluable way to find the right tag in the globally accepted taxonomy of mechanical ventilation modes. And Professor Chadburn is the founder of the taxonomy of mechanical ventilation, which is globally accepted. He is the founder of the SEVA training program. But also he provided a beautiful app, the VMM app, and you can download this for free from the App Store. And in this way you can find for the ventilation mode you use, the vendor you use, exactly the right tag. And in this way you can compare your ventilation mode in a fair way without commercial interference with the other ventilation modes. And now you can use your strategy, your ventilation strategy, you can adapt on really the capabilities of the ventilator. So that's very important. So it's also important to tag flow-controlled ventilation in the global taxonomy, because this is the only way to express why FCV is such a unique ventilation mode. There are more than 300 ventilation modes available commercially, and many of those names point to exactly the same tag. So here you see a lot of different ventilation modes, all pointing to the same tag. And even worse, we have to speak the same language, because if you use wrong terminology, this will lead to ambiguity to the users of FCV and also to misunderstandings. Why is the respiratory rate so high? Why go tidal volumes go down? This can be explained fully by the characteristics of flow-controlled ventilation. And to show how challenging it can be to find the right tag in the taxonomy, I first asked ChatGPT to provide me the correct tag in the taxonomy of Professor Chadburn. And he gave me these discriminations, and the control variable is flow. The breathing frequency is a continuously mandatory ventilation mode. The targeting scheme should be the targeting scheme should be dual loop. And your triggering should be time, and your cycling should also be time. And keep these discriminations in mind. So we start with the first control variable. What is FCV? And the first control variable means how do you control your breath? This can be in two ways. You can have a fixed pressure. This means your volume will fluctuate based on compliance resistance, characteristics of the patients, or you have a volume controlled mode, and this means your pressure will fluctuate based on compliance resistance. So you can choose one of those. So what is the control variable of flow controlled ventilation? Very surprisingly, because the inspiratory curves look quite similar than a volume controlled mode. And moreover, you set a fixed flow. But still, flow controlled ventilation is a pressure controlled mode. The only thing you can set is your peak pressure. And the rest, how fast peak pressure is reached, is fully depending on compliance and resistance of the patient. So a ventilation mode is not only settings, it's the interaction of settings of the ventilator together with the physics of the patient. So how fast the peak pressure is reached is based on the elastance. So your volume is based on elastance, and flow can be based on resistance. That's the equation of motion. And you see when peak pressure is reached, immediately the phone cycles to the expiratory phase. And even more interesting, The next step is the breath sequence, and the breath sequence tells you the interaction of breaths over time. This can be mandatory by the ventilator, fully controlled by the ventilator. This can be a spontaneous ventilation mode, fully initiated by the patient. And it can be intermittent mandatory ventilation. So then there is an interaction between spontaneous modes and controlled modes by the ventilator. And we all believe maybe flow control ventilation must be a controlled mandatory volume as breath sequence. But the opposite is true. The flow control ventilation is a continuously spontaneous ventilation mode. But we directly go to the conventional ventilation modes. And in conventional ventilation modes, you need first to trigger, the patient needs to be a sort of triggering. At least he has to extract some flow or to reduce some pressure to trigger the breath. But in this case, in flow controlled ventilation, the patient can't even have triggers. But just to reach your peak pressure based on compliance resistance will trigger the patient to the ventilator to the expiratory phase, and when reaching the EEP, the EVONE will trigger the inspiratory phase. So it's fully depending of an interplay between your pressures and your physics. So your phase variables that directly related to your breath sequence is not time, but it's all patient triggered. So your reaching EEP means you trigger to the inspiratory phase. Reaching peak, then you directly cycle to the expiratory phase. So it's not controlled by the ventilator by time or by volume, but fully on compliance resistance, fully on physics of the patient. And now you directly understand why the EVONE can result in high frequencies and low tidal volumes. It's just a wrong adaptation to physics and driving pressure and flow. So the cycle is also patient triggered, not based on volume, not based on time. And the third variable is the targeting scheme. How do you want to design your breath? What is your ventilation strategy? And your ventilation strategy can be based on a closed loop system, on a feedback system of the ventilator. But in this case, you look directly to the patient, and the only thing you can change your ventilator settings, your strategy, is do it yourself. So there is no feedback system on the phone, there is no closed loop system on the phone, so the ventilator will not adjust your the ventilation strategy, but you can say, okay, there is nothing protocolized in it, but still, there's a very individualized ventilation mode. You have to look directly to the patient, directly to compliance resistance, and in this case, you can adjust the settings yourself. So there is no closed loop then, so it is a set point targeting scheme for this moment. So we have almost all the discriminations, PC, CSV, set point. And the last discrimination, you have seen this picture more, is the most impressive discrimination, and this is the expiratory flow control. And this is never done in the world before. You control the expiratory flow by a continuous linear flow. And where you can say, okay, it's not the same than the volume control mode. And you can say the inspiratory curves look quite similar than the volume control mode, but the expiratory curves are totally different. You see a gradual decrease from peak pressure to your end expiratory pressure. You see the continuous flow, and you see a very stable gradual decrease from your maximum inspired tidal volume to your end expiratory lung volume. So if you compare this with the conventional ventilation modes, where you first find in conventional ventilation mode all the plateau phases, and in flow controlled ventilation, there's always a gradual, stable gas flow with relative low flows. So that means a lot for intratracheal pressures, for diaphragm movements, for lung movement, we come to that. So that's first. The second one is when you cycle from the inspiratory phase to the expiratory phase, you immediately get a pressure drop in volume control, pressure control. And you can say, okay, there is stress and strain in the inspiratory phase, but this is also direct collapse during the expiratory phase, when you look to dissipated energy. And the most important, maybe the most obvious, is the continuous flow during the expiratory time. And where you have a flow curve totally designed in the conventional ventilation modes, totally designed based on obstructive diseases, where you have a prolonged exhalation, or the restrictive diseases, where you have to keep down your peak flow, to reduce your peak flow. So you balance in a much more efficient way the long time constants and the short long time constants. And this is also a very interesting concept because it can lead to ambiguity. We always say in flow-controlled ventilation, your minute volume is the half of the flow. But it's not really the case. The reality is your minute volume is your flow times your duty cycle. And your duty cycle, the half of your flow in flow-controlled ventilation is only true when your inspiratory-expiratory time exactly are the same. But we know when we use the EVONE, this can be also EA ratio 1 to 1.5. In this case, you will never achieve your minute volume. So the set button of EA ratio set is not really a setting, it's a goal. It's what we try to achieve because 1 to 1 is the most physical way of ventilation. So we don't touch that button, but we, again, depending on physics. So it's more an interplay of the expiratory flow, the controlled expiratory flow of the ventilator, but also of the time constants of the lungs. And therefore, when you see the minute volume not reached, it's not really the correct alarm, because you have reached your minute volume, but not as you expected, because you would like to have the half of your minute volume, but it's not your half of your minute volume, but because your A ratio is different, not exactly 1 to 1. So have we found the Holy Grail? And Professor Anderman explained it already perfectly. I think we are more shifting from statical measurements, fixed tidal volumes, ideal body weight, which can be very confusing when you talk about the baby lung. It's totally different than a full open lung. And also statical measurement as plateau pressures, driving pressures. We much more go to stress and strain, but not only stress and strain, especially in time. And EVONE FCV fits perfectly in this concept because flow going, how fast is flow going? How fast do your repetitions? If you have very gradual, with a slow respiratory rate, gradual lung movement, it will be much more efficient than in conventional ventilation. So we go much more to dynamical stress and strain. Also, if you cannot maintain an A ratio 1 to 1, and you need a much higher expiratory time, for instance, for obstructive patients, for COPD, this means you have to reduce your inspiratory phase. When you reduce your inspiratory phase, this means you need more flow for the same tidal volume. And you avoid all those issues with flow-controlled ventilation, so you level in a much more efficient way the lung compartments. And therefore, avoid shear stress and strain. So then we look to the mechanical power and the dissipated energy. I hope that was enough for you to explain. So when we talk about the PV loop, the EVONE is a very accurate measurement device. And if you want to optimize based on the PV loop, you want to find the optimal compliance curve to be below the upper reflection point, to be above the lower reflection point, you need a stable situation with low flows and a stable inspiratory-expiratory phase. Otherwise, you don't have your perfect compliance curve. And with EVONE, you don't not only measure your driving pressure deep tracheal as deep as possible, so you have the real airway pressures. You also have a stable inspiratory phase and expiratory phase. And together with low flows, this gives the optimal compliance curve. So, is FCV unique? I asked the app because I'm biased. So I asked the app, is flow control ventilation unique? So I filled in the vendor, I filled in the mode, I filled in the FCV, the EVONE, and I asked the app, okay, what is the tag? And this is the tag we just discussed. So the academical tag. And then I asked, okay, are there more ventilators? Are there more ventilation modes in the world who do the same? And there is no comparable ventilation mode, ventilator found, although we discussed about more than 300 ventilation modes in the world. So no comparable ventilation found. So that brings us the unique. Why do we discuss in the beginning of the day ICU patients? Then we go to laparoscopic patients. Then we go to shared airways, small lumen ventilation. All these characteristics brings us to many applications which is never done before. Because for 70 years there was mainly focus on the inspiratory phase. And also research ongoing on the stable intrathoracic pressure swings, on intracranial pressures, and negative PEEP on intracranial, because you can control the expiratory phase. And it brings us to all these, on the first side, very, very different applications, where the added value of flow control ventilation in the shared airway and even in the emergency airway is to ventilate through very small bore tubings without the need for an open airway. In jet ventilation, it's impossible to do this. But also for ablations, you need stable thoracic diaphragm swings, thoracic swings and diaphragm swings to reduce organ movements. For the cardiothoracic, as Professor Ali explained, gas exchange, ventilation perfusion, optimal gas exchange, reduction of stress. For the ICU, also to minimize mechanical power, to go to level the long time constant, short time constant. For obese and for laparoscopic surgery, it's important to avoid diaphragm back. If you have a conventional ventilator and the expiration valve opens, directly you get all the abdominal pressure will remove your diaphragm upwards. And also collapse of the smaller airways. You keep the smaller airways in a much better way open. And the opposite is COPD. But in this case, the added value of flow control ventilation is to overcome the high resistance and to reduce your expiratory time. And to even support and maybe treat air trapping and hyperinflation. So a very different approach, but this is the uniqueness of flow control ventilation, in my opinion. And finally, I hope you can remember what I asked ChatGPT, because ChatGPT knows everything, how challenging it is to explain what FCV really is. None of the discriminations of ChatGPT were the same as the globally founder of the ventilation mode and the respected expert mechanical ventilation. So none of the discriminations were the same. That's it.